Welcome back to the course of applied elasticity. In the previous lecture, we were talking about the introduction to tensor algebra. We will continue with the same topic, tensor algebra, in this particular lecture as well. So, in the previous lecture, we had discussed about the summation conventions followed by introduction to Kronecker delta and permutation symbol. Now, we are going to give the definition of the second order tensor. So, second order tensors are basically defined as a linear transformations that maps one vector into another vector with the help of this particular transformation law. So, here T is a second order tensor which is acting over a vector A, and that results a new vector B. So, both A and B, these are two vectors, and here we are defining the vectors with one curl on top. This refers to a vector, whereas second order tensors are referred with two curls on top. So, this T is a second order tensor. So, definition of second order tensor is given by this particular linear transformation T acting over a vector A is resulting another vector B. So, you should understand that T is kind of an operator, but it is a linear operator. Now, in the with the help of summation convention, this can be written as T I j A j equals to B I, where I is the free index and j is the dummy index. I appears once in all the terms, j appears twice on the left hand side term. So, the summation is assumed over j for the left hand side term and I is the free index here. Now, coming to the properties of this linear transformation or the second order tensor. As it is a linear transformation, this follows the laws of linear superposition. So, if you consider two vectors A and B, and then this tensor T is acting on A plus B, that will be equals to summation of T acting over A plus T acting over B, the individual operators. This is the first property of linear superposition, and second property is T acting over alpha times A, alpha is a scalar, is equals to alpha into T acting over the original A vector only. So, these two properties are satisfied for the case of second order tensors, which is basically a linear transformation which transforms any vector into another vector. Now, coming to the components. So, in this equation T I j, these T I j are the components of a tensor. I and j can take values 1, 2 and 3. So, we define the components of a tensor for any chosen base vector E1, E2, E3 with the help of this kind of equations, where this tensor T is operating on the unit vectors E1, E2 and E3. So, if T is acting over unit vector or base vector E1, that results three terms T11 E1 plus T21 E2 plus T31 E3. Similarly, if T is operated over second base vector or unit vector E2, that will result three extra components T12 E1 plus T22 E2 plus T32 E3. Similarly, if we act T on E3, the third base vector, then that would result T13 E1 plus T23 E2 plus T33 E3. So, with the help of these three transformations, when the tensor is acting over the three base or unit vectors, with the help of that we can define the tensor components. So, first equation, three terms can be combined or condensed to a single term with the help of summation convention as T j1 E j, whereas second one is T j2 E j, third one is T j3 E j, and all three of them can be combined with a single tensorial equation as T acting over EI equals to T j I E j. So, with the help of this particular equation, we can define the tensor component T j I. So, T acting over unit vector EI equals to T j I times E j. Now, coming to the definition of dyadic product or tensor product of two vectors. Consider two vectors A and B. Their dyadic product or tensor product is defined through this transformation rule for any other vector C defined in the vector space as A dyadic B acting over C is equals to A times B dot C. Here C is any arbitrary vector in the vector space and this particular sign, this is called the dyadic product sign. So, A dyadic product B acting over C. So, this A dyadic B is basically a tensor. This is resulting a second order tensor which is acting on any arbitrary vector C and that would result A times B dot C. So, B dot C is a scalar. So, right hand side is a vector. On the left, one second order tensor is acting over a vector. So, left hand side is also a vector. So, dyadic product or tensor product is defined with the help of this particular transformation law for any two vector A and B. Now, with the help of this dyadic product, we can define the components of a tensor. So, as this transformation is linear and the dyadic product of these two vectors A and B is a second order tensor, any second order tensor can be written in terms of its components with the help of dyadic product as T tensor equals to T m n E m dyadic E n. So, E m and E n are two basis vectors. We are taking the dyadic product of two base vector E m E n that multiplied with the corresponding tensor component T m n. This would result the second order tensor T. So, definition of tensor component with the help of dyadic product is given by this particular expression. Now, we will try to prove this with the help of the definition of the dyadic product. So, T E I dot T acting over E j, we are starting with this expression. Now, T acting over E j is simplified and for that this particular dyadic product definition of T is replaced. So, T in this equation is written as T m n E m dyadic E n, that is acting over E j and outside we have dot product of E I. Now, this part can be simplified with the help of definition of the dyadic product. So, that would result E I dot T m n E m E n dot E j. So, these two are equal. So, this part E dyadic E n, E m dyadic E n acting over E j is becoming E m into E n dot E j, and E n dot E j dot product of two base vector E n and E j is nothing but delta n j, Kronecker delta n j. So, this in total becomes E I dot T m n E m vector delta n j. Now, T m n and delta n j both are scalar quantities, and with the help of the property of Kronecker delta, these two T m n and delta n j can be combined to a single term of T m j. N is replaced with j here as it is multiplied with the Kronecker delta. So, that overall expression becomes E I dot T m j E m. Once again, T m j is a constant that we can take out, and E I dot E m, this is nothing but delta I m. So, T m j times delta I m, once again using the property of Kronecker delta, this is equals to T I j. So, E I dot T acting over E j, this is equals to T I j. For any tensor, its component T I j can be written as unit vector T I dot the capital T tensor acting over E j. This expression defines the component of any tensor which can be obtained with the help of dyadic product. Now, coming to the definition of identity tensor. So, identity tensor is a tensor which transforms a vector into the same vector, and it is denoted with the help of this I. So, this I is used to denote the identity tensors. Now, by definition, as the identity tensors transforms any vector into the same vector. So, let us consider a vector A. Identity tensor acting over a vector A would result the same vector A as written here, I acting over A is equals to A. Now, by the definition of tensor components, T I j is E I dot T acting over E j. So, similarly, we can write I j, the ith jth component of identity tensor I as E I unit vector dot capital I identity tensor acting over E j. Now, by definition of identity tensor, I acting over E j would result only E j. So, this expression would be E I dot E j, which is Kroneker's delta, delta I j. So, the components of the identity tensor capital I, those are nothing but the components of the Kronecker delta, delta I j. Now, coming to different tensor operations. So, first one is the summation of two tensors. Any two tensor having the same order can be summed up, and that would result another tensor of the same order. So, T s and S being two second order tensor, their summation would result another second order tensor W. So, T plus S equals to W, and in the initial notation it can be written as T I j plus S I j equals to W I j. If this T plus S summation of two tensor is acting over any vector A, that would be equals to the two individual tensors T and S acting over A individually and then summing them up. So, T plus A acting over T plus S acting over A equals to T acting over A plus S acting over A, and also this can be written as W acting over A if W is defined to be T plus S. Now, coming to product of any two tensor. So, product of any two tensor is defined like this: T times S, T and S are two second order tensor, T times S is a new second order tensor that is acting over a vector A, and it can be defined as S acting over A, this will result one vector, and then T would be acting on that vector. On the other hand, if S is appearing first in the product, S times T acting over A is S acting over T acting over A. So, out of these two tensors whose product we are taking, any one will be picked up, the second one that will be acting on the vector first, and then that output that will be subjected to the second tensor operation. Now, T into S I j, the component of the product of two tensors T s. To obtain this, we are first using the basic definition of tensor components, E I dot T s times E j. Now, this particular part T s E j is written as S acting over E j, and then T operator is acting over that. Now, S acting over E j can be written as S k j E k by definition of the tensor components acting over the unit vectors. Now, S k j is a scalar here that we can take out, and this T operator will be acting over E k. So, if we are taking out S k j, then it would be S k j E I dot T acting over E k. Now, this total thing E I dot T acting over E k, this is nothing but the tensor component T I k by definition of the tensor components. So, T S I j, the components of the product of two tensor T and S, this is equals to T I k S k j. So, the first index of the first tensor is same as the first index of the product, second index of the last tensor is same as the second index of the product, whereas second index of the first tensor and first index of the second tensor, these two are same and that is a dummy index. So, T S I j is equals to T I k S k j. This is the form of product of two tensor with the help of the indicial notation or its components. Now, coming to the transpose of a tensor. So, transpose of any tensor T which is denoted by T transpose, another capital T written on the superscript. This is defined to be a tensor which satisfies the following identity for any two vectors A and B. If A dot T acting over B can be written as B dot T transpose acting over A, then T and T transpose are the transpose of each other. Now, A and B being two arbitrary vector, we can choose them to be anything. So, let us choose A as E j and B as E I, two unit vectors, and replacing them in this particular identity, it will become E j dot T acting over E I equals to E I dot T transpose acting over E j. So, with the help of this identity, E j dot T acting over E I equals to E I dot T transpose acting over E j, and using the definition of tensor components, the left hand side term can be written as T j I, right hand side term can be written as T transpose I j. So, this defines the transpose of a tensor components. T transpose I j is equals to T j I. Basically, here we are flipping the two indices. I is going in the location of j, j is going in the location of I, and also transpose of product of two tensor T S transpose follows this particular identity S transpose T transpose. So, T S transpose is equals to S transpose T transpose. So, the order in which these two tensors are appearing on the right hand side is flipped. Now, coming to the definition of inverse of a tensor. For any given tensor T, if another tensor S exists such that product of S and T is equals to an identity tensor I, then we call that S to be inverse of T. So, S times T is equals to I, S equals to T inverse. If we multiply both the sides with T, the left hand side will become S times T, whereas right hand side will become T inverse T, that is equals to identity tensor I. So, this is the definition of tensor inverse, and this exists only if determinant of this second order tensor T whose inverse we are taking is not equals to 0. If determinant is equals to 0, then tensor inverse cannot be defined. Now, coming to the definition of an orthogonal tensor. An orthogonal tensor Q is defined as a linear transformation for which the transform vectors preserve their length as well as the internal angle between them. Let us consider two vectors A and B. Now, by definition of this orthogonal tensor, if we are having Q acting on A, so A was the original vector, magnitude of A should be equals to magnitude of Q acting over A. So, A was the original vector, Q acting over A is the transform vector. The magnitude of both of them must be same by the definition of orthogonal tensor. So, Q A magnitude is equals to magnitude of A. Now, coming to the second point or second definition point, which is the angles between two vectors are also preserved. So, let us take two vectors A and B, and their angle is basically defined as their dot product. So, A dot B is equals to Q times A dot Q times B. If these two transformations are satisfied, then Q can be defined as an orthogonal tensor. Now, if you simplify the second expression, the second point, A dot B can be written as AI BI, whereas Q acting over A dot Q acting over B can be simplified as Q I J A J dot Q I K B K. Now, here writing A j at the beginning and B k at the end, it can be written as A j Q I j Q I k B k. Now, this particular term I and j locations are now flipped by the definition of transpose, and we are writing this as A j Q j I transpose Q I k B k. Now, left hand side of this equation A I B I equals to this particular expression. Now, right hand side is taken towards the left hand side. So, A I B I minus A j Q j I transpose Q I k B k equals to 0. Now, in the first term, this A I B I, this can be written as A j B j, because I and j both are dummy index. This can also be written as A j delta j k B k with the help of a Kronecker delta, where j and k are identical. So, the first term is written as A j delta k j B k minus second term remains as it is. Now, taking A j and B k common, and for any arbitrary vector A and B, for this equation to be 0, we must have delta k j equals to Q transpose j I Q I k. That means, Q transpose Q is equals to identity tensor. This is the definition of orthogonal tensor. For any orthogonal tensor Q, this identity must be satisfied. Q transpose Q is equals to identity tensor. And from that, taking Q on the right hand side, keeping only Q transpose on the left, Q transpose can be shown to be equals to Q inverse. This is also another property of the orthogonal tensor. Now, Q transpose, that is equals to Q transpose Q is equals to I. If we take the determinant of this equation on both the sides, left hand side will be product of two determinants, determinant of Q and determinant of Q transpose, whereas on the right hand side determinant of identity tensor I equals to unity. Now, determinant of Q is same as determinant of Q transpose, and thus left hand side is square of the determinant of Q, and that is equals to 1. So, determinant of Q, determinant of an orthogonal tensor can be either plus 1 or minus 1. Now, if determinant of Q is plus 1, then physically Q refers to a rotation tensor. If this determinant is equals to minus 1, then the Q refers to a reflection tensor. Now, after orthogonal tensor, we are going to talk about the symmetric and anti-symmetric tensors. Any tensor T can be called as a symmetric tensor if T is same as its transpose. So, if T equals to T transpose, we call T to be a symmetric tensor, and in the initial notation that can be expressed as T I j is equals to T j I, and T can be called as an antisymmetric tensor if T is equals to minus or negative of T transpose, and thus T I j its component is equals to minus of T j I. So, if T and T transpose are same, then it is called the symmetric tensor. If T is equals to negative of T transpose, then it is called anti-symmetric tensor. Now, any tensor T can be written as a summation or superposition of one symmetric tensor and one antisymmetric tensor. So, consider any tensor T, and that is sum of two tensor, one is T s another is TA. TS stands for symmetric tensor, TA stands for anti-symmetric tensor. So, TS plus TA will give the total T. Any tensor can be written in terms of TS plus TA, where T is the symmetric part which is defined as T plus T transpose by 2, and TA is the anti-symmetric part which is defined as T minus T transpose by 2. Now, corresponding to all the anti-symmetric tensors, we can define a vector quantity known as dual vector for that anti-symmetric tensor. So, let us say this small t with superscript a, this is the dual vector for the anti-symmetric tensor capital T. So, we are considering one anti-symmetric tensor capital T which is having a dual vector small t with superscript a. Now, how is this dual vector defined? If small a is any other vector, if I operate capital T, the anti-symmetric tensor capital T on any vector small a, and that can be expressed as small t, the dual vector cross small a, that arbitrary vector. If this relation is valid, for such cases small t can be named or called as the dual vector of the anti-symmetric tensor capital T. So, for any vector a, these expression if it is valid, then small t superscript capital A is the dual vector of the anti-symmetric tensor T. Now, if I write it, expand this in the matrix form, all these three equations if I write, then component wise the anti-symmetric tensor T can be written like this. For the anti-symmetric tensor, it must satisfy this property, Tij is minus of Tji. So, for that particular case, all the diagonal elements must go to 0, then only for the anti-symmetric tensor Tij equals to minus Tji can be satisfied. So, all diagonal elements for all anti-symmetric tensors are 0, and non-diagonal elements, these cross elements are equal with the opposite sign. So, these 0 T12 T13 minus T12 0 to T23 minus T13 minus T23 0, this refers to typical anti-symmetric tensor multiplied with this A1, A2, A3, the components of the arbitrary vector small a, and that would be equals to the cross product of dual vector and this small vector small a. So, the components of this cross product of these two vectors can be written as T2 A3 minus T3 A2, second component is T3 A1 minus T1 A3, and third component is T1 A2 minus T2 A1. So, using this equation, the components of the antisymmetric tensor are related with the components of the corresponding dual vector. Now, this equation can be simplified on the left hand side by taking the product of this T matrix and the A vector, and then in the initial notation this can be written as Tia. The ith component of the dual vector is equals to minus half of permutation symbol Eijk Tjk. So, simplifying this expression, we are getting these three components of the dual vector. Now, if we expand this initial notation with I equals to 1, T1a would be minus half of E123 T23 minus half of E132 T32, and this would be minus T23 by 2 minus T23 by 2. In total, this is minus T23. Why? Because this fellow is equals to minus 1. E132 is minus 1, E123 is 1, and with the property of antisymmetric tensor, T32 is minus T23. So, this expression can be expanded, and with that we can show that all the components of the antisymmetric tensor can be represented with this equation. T I A, dual vector of an antisymmetric tensor, is equals to minus half of permutation symbol E I j k T j k, where T is an antisymmetric tensor. Now, coming to the eigenvalues of a tensor. If a vector A transforms under linear transformation T into a vector parallel to itself as T acting over A equals to lambda times A. So, the T acting over A, the resultant vector is parallel to actual vector A with a scaling factor lambda. Then we call that lambda to be the eigenvalue and A to be eigenvector of the second order tensor T. For definiteness, we assume all the eigenvectors to be of unit length, and n being the unit eigenvector, this expression becomes T n, T acting over n is equals to lambda times n. Now, n equals to alpha j e j. As n is unit eigenvector, we define this alpha with the help of this expression alpha j equals to 1, where n is alpha j e j. So, alpha j are the components of unit normal vector eigenvector n. Now, with this, with the help of this n as a j e j, we can write this expression T acting over n equals to lambda n in the initial notation as this T I j minus lambda delta I j alpha j equals to 0. So, lambda times n is written as lambda times identity tensor I acting over n, and that I is here represented as delta I j. Now, if I expand this and write all three equations separately, then it will be of this particular form. Now, these three equations can be condensed to a single determinant equation, determinant of T minus lambda I is the identity tensor, equals to 0. So, determinant of T minus lambda I is 0. This is known as the characteristics equation of second order tensor T, and by solving this we can obtain the all the three eigenvalues lambda for this particular second order tensor T, and then putting those lambda values back in these three expression, we can get the components of alpha 1, alpha 2, alpha 3, which would help us to determine the eigenvectors A. So, in this particular lecture, we had discussed about the definition of second order tensor, followed by different tensor operations. We had also discussed about the orthogonal tensor, symmetric, antisymmetric tensor, and eigenvalues of the second order tensors. Thank you.